Hi everyone, am I audible to all of you? Can you hear me? Okay, it's fine. Uh, in previous lecture, I have discussed about all the closed loop transfer function, and as well as I have discussed about the integral, different controller, let's say proportional controller, proportional integral controller, and PID controller. And I had started the how we can, uh, how these controller affects our output, right? And why we use controller, all these things that we are going to study today in this particular lecture. So again, I'll be talking about closed loop transfer function, and in which I'll be taking different kind of processes, let's say first order process, second order process, and I'll be controlling that first order process and second order process with the help of proportional integral and PID controller, all these things, and a combination of uh, proportional integral or PID, and all kind of thing, right? So let's try to understand how we can understand. So in the previous lecture, I was talking about if this one is input, let's say input is our X, right? So let's say this is the transfer function GC of controller, and this is transfer function of final control element, and here there will be a load, that one is U, right? And let's say this one is your process, right? And what happens, this one is your output, fine. And after that, what happens, this output will be feedback to the input, and this is measuring instrument. Sorry for that. So again, this topic is very important topic. Oh, just wait 1 second. I don't know what is happening to me. This will be- yeah, yeah. So again, yeah. So again, this will be a feedback over here, right? So and I'm assuming this one is a negative feedback, right? So I hope you people know these things very well now. So what is happening? This one is your process, right? This is general block diagram of closed loop transfer function. This one is your final control element. This one is controller. X is your input, and this is called as the set point. U is called as the load, and this one is your measuring instrument, and this one is your output, right? And this is a closed loop transfer function. So if I want to know the transfer function of closed loop, so this will be equals to y upon x, and that is called as a GS. And this one is ys upon xs. So this one is your output, and this one is your input GS. So in the previous lecture, I told you how can I understand these things. So that will be equals to GP GC GF divided by 1 plus GP GC GF GM. Now I'm not going to solve all these things. Just I will be writing directly. So let's say here, if GM is equals to 1 and GF is equals to 1, right? I'm assuming the transfer function for measuring instrument and final control element is equals to 1, right? And if I am assuming GP, that is the transfer function of process, and I am assuming this one is a first order process, so Kp upon tau Ps plus 1, and this one is Gc, that is transfer function of your controller. I am assuming here the transfer function is a Kc, which is your proportional controller. I hope you must have understood this thing. So now I'll be substituting all these value over here. So now I can write that Ys divided by Xs, that is equals to, here GPGC it was there. So that is Kc into Kp upon tau Ps plus 1 divided by 1 plus Kc into Kp upon tau Ps plus 1. Right? So I can write here Kc Kp. So I'll tell you the gain in the transfer function. Just wait over here right now, right? So after the this particular once you will solve this particular thing, you will get the value of gain over here. So KPKC divided by the value will be tau PS plus 1 plus KPKC. So finally, if I'll divide 1 plus KPKC in the numerator and denominator, so what will I get? KPKC divided by 1 plus KPKC divided by tau p upon 1 plus kpkc plus 1. So now you can see this is the transfer function of our, that is you have got ys upon xs, right? That is equals to kpkc divided by 1 plus kpkc and upon tau p upon, sorry, here it will be s 1 plus kpkc into s plus 1. So if I compare these things, so you will get kp dash, that is equals to what? kpkc upon 1 plus kpkc. And if I want to know tau p dash, that is equals to tau p upon 1 plus kpkc. So this is called as the gain of transfer function, and this is called as the time constant of transfer function. When P controller, only P controller is introduced into the closed loop transfer system, right? And here you see, since Kp is greater than 0, Kc is greater than 0, so what happens? All of these is positive. So can I say Kp dash is equals to, I mean, again, what you can see over here is Kp dash is equals to what? If I'll increase Kp, let's say, our controller gain is Kc, right? Our gain of the controller is Kc. Let's say our Kp is constant, right? Let's say Kp is constant and Kc I am going to vary. So what will happen on the Kp dash? So if Kp is constant, what happens? If I divide Kp Kc in the numerator over here, so what happens? 1 upon 1 upon Kp Kc plus 1. Fine. So what happens? If I'll increase Kc, Kc is increased. What happens? If I'll increase Kc, so this will decrease. If this will decrease, what will happen? Overall, this system will increase. So if I'll increase Kc, what happens? Kp dash will increase. Means if you increase the if you will increase the gain of the controller, what will happen? The overall gain of the closed loop transfer function increases. Is it clear? So this Kp dash, I have told you the gain of the transfer function. So if Kc is increased, what will happen? Kp dash will increase. Is it clear? So while increasing the gain of proportional controller, the overall gain of closed loop response increases. right? I hope these things is clear to all of you. Now, coming to that tau p dash is the overall time constant of the closed loop response. So that is equals to 1 plus Kp Kc. So since I told you that Kp is constant, so if I will increase Kc, what will happen? The denominator will increase, so numerator will decrease. So your tau p dash will decrease. So if tau p dash is decreasing means what is happening? So response will become fast. So let's say if our response was yt, if it is giving in 10 seconds, now it will give in only 7 second, 8 second like that. So our response is getting faster, right? So what happens over here? So now the thing is that what we need to understand, since we have got that ys divided by xs, that is equals to kp kc divided by tau p upon 1 plus kp kc plus 1. Is it clear? And divided by 1 plus kp kc. So let's say I am giving a unit step input 1 upon s, right? So what happens? Ys that is equals to 1 upon s into, I'll write directly kp dash upon tau p dash s plus 1, right? So what happens? If I'll convert s into t, then I'll take Laplace. Let's say this one is your equation 1. If I'll take Laplace over here, so what will happen? Yt is equals to what? Kp dash into 1 minus e to the power minus t by tau p dash. Fine. So your yt. Now the thing is that just try to understand over here. So the response will look like that. So now here this one is your yt and this one is your t. So at t tending to infinity, what will happen? Response will look like kp dash. This one is your kp dash. So it should be going like that. It will go like that. But now what happens? I'll check effect of Kc. So if I am increasing Kc, what is happening over here? Kp dash is increasing, right? Kp dash is increasing, and if I am increasing Kc, what is happening? Tau p dash is decreasing. Are you getting it? Kp dash is increasing and tau p dash is decreasing. So the thing is that you will see there is this kind of plot would be there. It will go like that. So I'm just drawing here. The thing is that, so what is happening? So let's say for a particular time, if I want to check whose KP dash is maximum. So this one is KP dash 1 Let's say KP dash 1. And for red one, this one is KP dash 2, KP dash 2. And for this one, last one, this one is your KP dash 3. So since here we see Kp dash 1 is greater than Kp dash 2 is greater than Kp dash 3 from the graph. And if I'll increase Kp dash, what will happen? Kc increase. So can I say that Kc1 is greater than Kc2 is greater than Kc3? So if I'll go from here to here, Kc will decrease. Is it clear? Kc1 is less than Kc2 is less. If for first it is Kc1, if if I'm going to change the Kc value for three kind of controller, what will happen? You will see this kind of plot will be there, and you can understand for this black one, Kc dash will be maximum, and for this blue one, Kc dash will be minimum. So Kc will be minimum. So this one is Kc3. So this will be the output that you will be getting over there. Once you are controlling a first loop, first order system with proportional Is it clear? So your response is becoming very, very fast if you are increasing the gain of controller, right? So that's the meaning over here. Now, here what we see when we try to control, uh, this one is your first order system, right? With proportional controller. Now, I'll be using integral controller plus first order process. So I told you the transfer function of integral controller that is equals to Kc by tau I into S. Is it clear? Transfer function is this one. So let's say this one is your controller and this one is your measuring final control element GF that is equals to 1, right? And this one is your process GP. You will be getting output, and this one is your comparator. From here you will be giving a input access. And this is a negative feedback system, so definitely the feedback loop will be there, and there will be measuring instrument having transfer function 1. I am assuming it can be anything, right? So here the error will getting generated. This one is your output. So again, so since the transfer function of controller, since this is integral controller, so that is 1 upon tau is, I am assuming, and this is in S domain, and this is a process, so I am using kp upon tau s plus 1, tau p s plus 1. This one is transfer function of process, and gfs is equals to gms is equals to 1. I'm assuming this one. So with the help of this one, I'll get ys upon x. This is the transfer function of the control, closed loop transfer function, and that will be equals to gp gcgf divided by 1 plus gp gc gf gm. Right? So here you can write kc upon tau I into s into kp upon tau ps plus 1 divided by 1 plus kc upon tau is into kp divided by tau ps plus 1. So again you have to do the mathematical operation for this particular thing, and we will get something, some good observations from here. So finally you will see that ys divided by xs is equals to kp kc divided by, that is tau is into tau ps plus 1 plus 1 kp kc. Fine. So again, I can write ys divided by your xs, that is equals to kp kc divided by tau I tau p into s square plus tau is plus kp kc. So I mean it seems like it is going to be a second order transfer function, tau square s square plus 2 zeta tau s plus 1 kind of thing. So I'll convert this into the standard form, right? So I'll be dividing kp kc in numerator and denominator both. So what will I get? That ys divided by xs, that is equals to 1 upon tau I tau p divided by kp kc into s square plus tau I divided by kp kc into s and plus 1. So now, since I can compare these things with what, that kp divided by tau s square plus 2 zeta tau s plus 1. This is a second order transfer function. Fine. So what will you see? The transfer function of closed loop response, that is equals to, here you can see the gain of closed loop, that is I am assuming that k dash is equals to what? 1, and tau dash, that is time constant of closed loop, right? So this is tau square. So this will be equals to root over tau I tau p divided by kp kc. And since 2 zeta tau dash, right? 2 zeta tau dash, that is equals to tau I upon kp kc. Since we got the value of tau dash, so I can substitute here. So 2 into zeta into root over tau I tau p divided by kp kc, that is equals to tau I divided by kp kc. So once, I mean, it will get cancelled out and again it will get cancelled out. So the thing is that you will get the value tau I tau p here, and this one is your tau I. Okay. So the value of zeta from here, what will you get the value of zeta? What will be the value of zeta? Can you calculate? This is just a simple mathematics now. I hope you people are getting it. So the value of zeta, that is equals to 1 upon 2 root over tau I divided by tau p kp kc. So you will be getting the value of zeta like that. Is it clear? So now what we have seen over here is that once you introduce an integral controller with first order transfer function in a closed loop, then the transfer, earlier it was a first order, but now this one is the transfer function of what? This one is the transfer function of your closed loop. Is it clear? This is the transfer function of your closed loop. So the transfer function is increased by a order of 1. If it was first order, it got second order. If it was second order, it will get third order. If it is third order, it will become fourth order. So the observation from here, what you can see, that if a first order process is controlled by a integral control, then the order of transfer function of the closed loop response become second order. So it will become second order. Now, the next observation is that our value of what? Tau p dash, tau dash, that is k, k dash is equals to 1. Third one, tau dash, that is equals to root over tau I, tau p upon kp kc. And the fourth observation, zeta is equals to 1 upon 2 root over tau I divided by tau p kpkc. Is it clear? Tau y divided by tau p kpkc. Fine. So this one is the observation. Now, what happens? There are two parameters of the controller over here. One is your tau I, because this is parameters of controller, and this one is kc, that is the controller gain. So two parameters of controller. That one is tau I and kc. Fine. So let's say if first case, if kc is constant and tau I is varying, then what will happen? What will happen? If tau I will increase, what will happen? Your tau dash will also increase. Is it clear? Since tau p and kp will be constant, because this is the parameters of process. So process will be same, but now I want to tune the controller. So to understand, to analyze the effect of the controller on our output. So that's what we will be changing the parameters of the controller right? So there are two parameters of controller that is involved in this particular transfer function of closed loop. One is t tau I and one is kc, that is gain of the controller and the time integral time constant for the uh, integral controller. So first I'll make kc constant. I'll change the tau I. So what will happen if I'll increase the tau I? Tau dash will increase. Now what is tau dash? The time constant of the transfer function of closed loop response. Closed loop response. So what will happen if we will increase the tau I? Response will become fast. Response will become fast. I hope this thing is clear. Now, second, Kc, I'll vary Kc and making tau I constant. So what will happen in that case? If I'll increase Kc, what will happen? Your tau dash will decrease. So what is happening over here? So increasing the gain of controller will decrease in the tau dash. That means response will become slow. Is it clear? So your response will become slow. That's what the case is over here. So again, it's very important to understand this particular thing over here. So the thing is that since this is a second order system, now these two are there. Now the value of zeta, third parameter that we are going to discuss, that is zeta. Zeta, the value of zeta is 1 upon 2 root over tau I upon kp kc tau p. So first, again here two parameters are there, tau I and kc. So first kc, I'll make kc constant and will vary tau I. So if I'll increase tau I, what will happen? Zeta will increase. Fine. Second one is if tau I is constant and I'll vary kc. Kc, I'll vary. What will happen? Zeta, if I'll increase kc, what will happen? Zeta will decrease. Right? So here, if I zeta is decreasing, means the response will become more sinusoidal kind of thing. So we have seen three things over here that we are having two parameters, that is zeta. One parameter is our zeta and one parameter is our tau dash, right? So here this was kc and this was your tau I, right? So what is happening over here? Zeta is if kc, if tau I is constant, right? I mean, you can understand these things in your own way, how you can make the table and you can understand these things. If I'll increase Kc, let's say if I'll increase Kc, tau I constant. And second thing you can make, if I increase tau I and Kc is constant, fine. So you can separate these things and you can understand, you can write the value of zeta and tau. And this is only valid for integral controllers with first order system. This is only valid for integral controller with first order system. I hope this thing is clear to all of. Fine. So here, what you see, if I'll increase the tau I, what will happen? Our response will become fast. If I'll increase the kc, our response will become slow. Right? So two opposing factor is working simultaneously. to understand the response fast, because ultimately we are very much interested in to making the response very fast for the particular system. So if I'll increase tau I, response will become fast. If I'll increase Kc, response will become slow. So